down here. Here we're concerned with the movement of tape in terms of the torque applied to the tape driving members and the back tension brakes that determine just how tape will flow. So our first series of adjustments will deal with brakes and torque. Some of the adjustments we'll be showing you require the emplacement of a master plane jig. Now this fits over the rotary head drum assembly lower part. There's a lug or a post that sticks up from the casting of the lower rotary head drum assembly that mates with a hole in the master plane jig. Now slide the jig in place so that it fits over the lamp assembly for the photocells and over that post. Now there's one screw that will hold it in place that goes into a threaded hole on the lower casting of the rotary head drum assembly. Any 3mm screw will do, as long as it has no captive washer. Now there's that white plastic cylinder that fits over the supply reel table, and that's used to locate the master plane jig. And the master plane jig fits tightly against that white cylinder. The screw that holds it in place can be snugged down. Now you can take off that white cylinder and the jig is ready for action. The height of the reel discs or tables is critical to proper tape flow. They lift the reels inside the cassette clear of the cassette floor and determine the altitude at which tape leaves the cassettes. To measure reel disc height, we use this gauge. It's a go, no-go gauge with two steps. When placed on the master plane jig, the outer step should clear the top edge of the reel disc, but the lower edge should be caught upon it. If both clear, it's too low. If neither clear, the reel disc is too high. Now that's the supply reel disc and it's right. Now we'll make the check on the take-up reel disc. Note that both steps on the gauge clear the top of the reel disc. So this disc is too low and will have to be raised. To do this, we'll remove the master plane jig and in this case take off the belt to the tape counter and take up sensor. Then we'll pry off the E-ring that holds the top of the spindle. Now the reel table can be lifted off. We might have to release the stop brake in this case and lift the table straight up. And we adjust the height of the gauge by adding washers as needed. In this case, the hold of the cassette disc was too low and we'll have to add a washer. There are 3 washers available at various thicknesses for this job. And you can try by trial and error to see whether or not they're needed. Make sure when you take the disc off that you don't lose any washers that might be sticking to it that had been there previously. Now we've added the washers and put the disc back in place. We'll check now for proper height. Now we put the master plane jig back in place and we'll check for proper height. And this time we've found it. The top step just clears, the bottom step just hits. We have to make the measurement in 2 different places to make sure. Loading brakes are applied to both the supply and take-up reel tables to ensure proper back tension while the loading cycle is going on. Now, in order to check the tension on those brakes, we're going to have to disable the photocells on both sides, and we'll also have to imitate a cassette being in place by closing that micro switch by hand. Now we're going to have to get the brakes on. In order to do that, we'll have to put the thing in the play mode but stop the machine by turning off power before the machine is fully threaded, before the arms reach their final position. Now the loading arms are halfway up and we've turned off power, and the threading brakes are now applied to both the supply and take-up reel side. Now we'll simulate a nearly empty supply reel by winding the tape clockwise on the hub of the dummy reel and putting it in place. Now we'll hook the tension gauge on the leader and pull the tape at approximately the right loading speed and measure the tension. Speed isn't really that critical, but the back tension should be between 40 and 50 grams. If the supply loading back tension is out of spec, it's necessary to bend this part of the bracket that holds the unloading idler. To reduce the tension, bend the bracket so that the idler moves away from the reel table. To increase it, bend the bracket in the opposite direction. The take-up loading brake can be checked with the machine under the same condition, that is, partially loaded. This time we'll use the dummy reel with the tape wound in the opposite direction, counterclockwise around the hub. We'll place it on the take-up reel table, use the same spring scale to check back tension as we pull tape at almost the normal loading speed. And the spec for this back tension is 30 to 40 grams under these conditions. If take-up loading back tension is out of spec, it's necessary to bend this point where the brake joins the bracket on which it's riveted. To reduce back tension, bend in this fashion so that the brake moves away from the reel table. To increase back tension, bend the bracket in the opposite direction. Now we're going to check rewind torque. To do this, it's necessary to put the machine in the rewind mode, but we have to fool system control into thinking that a cassette is in place. For this reason, depress the play switch, the second micro switch from the right at the top of that bracket. Now we put the torque meter in place over the supply reel table and let the torque meter slip gradually through your fingers as you read the instrument. Minimum torque is 270 grams. We have a reading here at approximately 400 grams, which is within spec. If rewind torque is out of spec, it's necessary to clean the pulleys and drive belts or the drive tire on the top of the chassis of the rewind idler assembly. If cleaning these components fails to restore torque to proper specifications, it's necessary to replace this entire assembly. This is the rewind idler assembly. In early versions of the 3300, the rewind idler assembly allowed some degree of adjustment of rewind torque. And that could be accomplished by replacing the washers under this E-ring. By changing the shim washers, torque could be adjusted. For detailed procedures, refer to page 5-8 of the 3300 manual. To measure fast-forward torque, it's necessary to put the machine in the fast-forward mode. No other action is necessary. Place the torque gauge over the take-up reel table and allow the gauge to slip slowly through the fingers while reading the gauge. And take-up torque should be in excess of 270 grams-centimeters for fast-forward. If fast-forward torque is below spec, clean the drive surfaces on the rewind idler, the fast-forward idler, and the rubber tire on the take-up reel itself. In later machines, the fast-forward idler also has a rubber tire mounted on it. To measure forward take-up torque, it's necessary to put the machine in the record mode. We can do that by disabling the record safety feeler and pressing both the record and play keys. And we'll let the machine run in this fashion for about 2 minutes until it stabilizes. Let's assume that the 2 minutes are up, and then we'll press the pause key. The take-up reel table will stop turning, but if we move this memory plate towards the back of the machine, then we will restore normal drive to the take-up reel table. Now we can measure take-up torque. And it should be between 80 and 220 gram-centimeters. Take-up torque for the 3300 requires a slightly different procedure. In this case, we put the machine in the play mode and we hold the micro switch S5, the pause micro switch, down to disable system control. Now we put the torque meter in place and allow the gauge to slip slowly through the fingers as you read it, and the specification is the same, 80 to 220 gram-centimeters. Take-up torque can be adjusted by means of this adjustable slip clutch. Those beryllium copper spring leaves can be made to rotate and fit on various steps. Turn them always in the clockwise direction. When they're on the highest steps, torque is maximum. When they're on the lowest steps, that is closer to the chassis, torque is minimum. In the 3600 and late model 3300s, the slip clutch looks a little bit different, but it works exactly the same way. Here's the slip clutch. In this case, the steps are on the side of that pulley facing the chassis, and the leaf springs are as well, but you can still push the leaf springs around to get to the appropriate steps. Now we're going to measure unloading torque, the drive to the supply reel in reverse during the unload cycle. To do this, we'll have to depress S2 and S4, the micro switches at the top of the function block. And we'll put the torque meter in place and allow it to slip slowly and read the unloading torque. It should be between 80 and 220 gram-centimeters. There is a mistake in the service manual. It says to depress S2 and S3. That's an error. It should be S2 and S4. If unloading torque is out of spec, it's necessary to clean the drive idler or this belt and its pulley on the unload idler assembly. If the unit continues to be out of specification, it's necessary to replace this entire idler assembly. There is some degree of adjustment on older 3300 models. The unloading idler assembly can be adjusted by removing the E-ring and adding or taking away washers just underneath the E-ring. Now we're going to check supply back tension. And this is done in two major steps. And to set up the conditions, we first put in place the master plane jig. Now we're going to load a cassette that has the supply reel practically empty, just a few turns of tape left on it. And we'll use the cassette holder in the jig kit, slip it under the brackets at both sides on the chassis to hold the cassette in place. Now we have to look at that extension of the master plane jig. And see where the arm of the back tension servo ends when we put the machine in the play mode. Now the space between that extension of the master plane jig and the arm of the back tension servo should be 1.5 millimeters. To adjust the final position of the play arm, we put the machine in the play mode, loosen the screw that holds this anchor at the tail end of the brake band. Now that anchor is moved to the left or right. It moves the tension arm as shown, and you can adjust the final position. Now we've removed the cassette to show this, but the adjustment should be made with the cassette in place as was shown earlier. Once we have the tension pole position set correctly, we can proceed to step 2 of the back tension adjustment. Now we've removed the reference plate, and we'll put the back tension cassette gauge in place as though it were a cassette. Clamp it in place with the cassette holder from the jig set and put the machine in the play mode. Now we can read back tension directly. This gauge is reading 32 grams. The spec is between 28 and 45 grams, with 35 being the ideal setting. If back tension needs correction, it's necessary to move the anchor connected to that spring. Spring connects at one end to the tension arm and at the other end to this anchor, very close to the front of the machine. The screw is out of sight at the moment. If you loosen the screw and move that anchor towards the back of the machine to reduce back tension, or bring it towards the front of the machine to increase back tension. The DC drive motors are subject to mechanical wear at the commutator and may require replacement after about 3,000 hours of operation. Of those two motors, the smaller one at the right is the drum motor, the larger one is the capstan motor. Now, to replace the drum motor, the entire bracket on which it is mounted is removed, and the new motor is installed in the bracket using those 3 screws at the top. Then the original pulley is put in place, and a 7/10 of a millimeter thickness gauge is used to set the distance between the top of the bracket and the bottom of the pulley to 7/10 of a millimeter. That feeler gauge won't go all the way in, but it'll go in about halfway, just enough to determine the distance correctly. And then using a hex key, the pulley is fastened in place. Then the entire unit can be replaced on the chassis. The capstan motor is mounted on the chassis directly using those 4 threaded holes at the top. When replacing the capstan motor, transfer the original pulley to the shaft and use a 1 millimeter thickness gauge to set the distance between the motor housing and the pulley to 1 millimeter. Now, the original 3300 service manual calls for a 1.5 millimeter spacing, and that's no longer true. It's 1 millimeter for both 3300 and 3600 capstan motors. Failure of either of the video heads requires replacement of the entire upper drum assembly on which both video heads are mounted. This is quite an easy job in the VHS. All that it needs is removal of 2 screws that hold the upper drum assembly down to the rotating platform underneath. And then 4 leads to the rotary transformers have to be unsoldered. Now, those are the small wires that come up through a pair of holes close to the spindle. Those wires go down to the secondaries of the rotary transformers immediately underneath. Now, when those wires have been unsoldered, you can pull the upper drum assembly straight up. Okay? Now, before you put the new assembly in place, inspect the top surface of that rotating platform and clean it with a lint-free cloth moistened with alcohol. Make sure there's no dust or wax or anything adhering to that top surface. Now put the replacement unit back in place. The tricky part of the job is feeding the rotary transformer wires up through the 2 holes close to the spindle. It's possible to put this head in backwards, that is 180 degrees from its normal position. But to avoid this problem, make sure that the wire colors on the leads coming up from the rotary transformer match the wire colors on that PC board on the upper drum assembly. The boss that locates the center of this assembly is very, very accurately machined, and it determines the concentricity of the upper drum assembly with the rotating spindle. In the design of the VHS drum assembly, factory has preset dihedral angle, head tip penetration, eccentricity, and video head azimuth angle. Now, all of these things are preset in the upper drum assembly, and the technician need not be concerned with them. Now, make sure the upper drum assembly is firmly seated on its rotating platform and turns freely. Then install the 2 screws that hold the upper drum in place. And make sure they're snug down. Now separate those wires that come up from the rotary transformers and solder them in place on those small PC boards in the upper drum assembly. Looks like asbestos fingers might help a little bit in this operation. After the head assembly has been replaced, there are a few electrical things that must be checked, and here they are. Video head switching position, both in playback and record, quick check of tracking, adjustment of cue and resonance of the video head inductance with the input preamp, FM channel balance, color channel balance in both playback and record, and the DOC level. If the audio or control or audio erase head require replacement, this assembly must be removed. Now, it's fastened to the bracket underneath by means of these 3 screws, A, B, and C, which must be taken out. Beneath those screws are 3 springs that hold that head assembly at the right altitude and angle. Take off the small PC board at the back and put it on the replacement head assembly, and then replace the unit on the screws or on the springs and put these 3 screws in. Now, adjustment of this head assembly is extremely critical because the 3 screws themselves determine the height above the chassis. The 2 screws here with relation to one another determine the azimuth angle, and this screw in the back determines tilt. If tilt is incorrect, tape as it on its way to the capstan will be forced upwards or downwards. So we'll have to make some rough adjustments to put the thing in place, and then we'll make some fine adjustments electrically for final location. Here's a front view of the assembly. After we've replaced the head assembly, we play a work cassette, actually play the tape, and adjust altitude, the height of the head assembly, using all 3 screws. Turn them the same amount so that the top edge of the audio erase and audio heads are just even with the top edge of the tape. That's critical. And the screw in the back, screw C, should be adjusted so that there's no curl of tape. The tape is not forced to move downward or upwards against this edge of the guide post just to the right of the head drum assembly. Now, these are rough adjustments, and we'll show you a little bit later how we can check electrical factors to see whether or not we have azimuth and tilt set correctly. We'll look at the RF envelope from the video heads for tilt adjustment, and we'll look at the high audio tone, the 7 kilohertz tone, for correct azimuth angle. When we're satisfied with rough adjustments, we'll monitor audio output at test point 23 on the audio servo board with an oscilloscope, or test point 15 if it's a 3300. Then we'll play the 7 kilohertz section of the alignment tape and adjust screws A or B for maximum audio output. Audio output will reach a maximum or peak when azimuth is set correctly. So make sure you go past the peak and set for maximum output. Now for a fine adjustment of tilt, we'll monitor test point 6 on the playback record board. That's the FM playback envelope. And we'll adjust screw C carefully to get the flattest possible envelope. If overall height changes, then it would be necessary to turn all 3 screws the same amount to get height back where it should be. Remember, tilt has a lot to do with the interchange capability of the machine, and we'll adjust the tilt for flatness of the envelope. Make the envelope as flat as possible. The final adjustment is tracking. To do this, we'll loosen these 2 screws shown in red here. They permit the control head assembly to be moved upstream and downstream in the tape path. We'll still be monitoring test point 6 on the playback record board, and make sure that the front panel tracking control is in the detented or auto position. Then we'll move this head very carefully upstream or downstream in the tape path and adjust for maximum RF output. When tracking is set correctly, the envelope will peak in amplitude and be at maximum flatness. This permits perfect interchange between machines. Now for a final check at the tape path. The tape path is extremely critical, and it should be set right so that interchange between machines can be performed. Now, the critical area is here because the altitude of the tape and its guide around the head drum assembly is determined principally by the anchors that the arms are pressed into. These should never be touched. Notice that they're fixed to the casting of the lower head drum assembly. So leave this area alone. It's extremely stable, very rugged, and if you try to make adjustments here, you're liable to get lost in a maze of errors. So when checking the tape path, look at this area. Follow the tape path. Look for curls or creases in tape. Make sure that the lower edge of the tape bears against the guide band at the bottom of the head drum assembly, and look for curls or creases of tape as the tape passes the control track area and the capstan pinch roller. Before attempting any adjustments, eliminate the easy things. One of them is the arm for the tape tension servo. That's somewhat vulnerable, so check to make sure that it's perpendicular to the chassis. You can do that by following the procedure in the manual that uses the master plane jig and the real height adjustment jig to check for perpendicularity. Also check the real heights. We showed you how to do that earlier. Look at the pinch roller. Make sure it's not worn, and if it is worn, replace it. And those are the things that should be checked if there's an error in the tape path. Leave this area alone. Finally, if there's an error in tape threading or unthreading, if the tape jams or curls in that process, confine your attention to this area, because the likely source of trouble is an error in back tension or torque. Preventative maintenance. In this section, we'll look at cleaning, lubrication, and some recommendations for component replacement. The first job of the cleaning process is to clean all the drive surfaces, all the rubber or plastic drive surfaces, and we'll use a lint-free cloth moistened with isopropyl alcohol. Supply reel table first. Hold the cloth against the rubber tire and turn the table with your finger. Now the unloading idler, same way. Rewind idler, and the drive surface of the fast-forward idler, which in later machines has a rubber tire. and the take-up drive surface. Now the purpose here is to remove traces of grease which might cause the drives to slip. And also the belts. You can hold the cloth against the belts, rotate the pulleys so that the belts bear against the dampened cloth. Now we'll take a look at the tape path. The purpose here is to remove oxide debris from the tape. We clean everything in the tape path, starting with the erase head, the surface of the erase head, the impedance roller on the entrance side of the scanner, the entire surface of the upper and lower drum. You can clean the upper drum by holding the cloth against it and rotating it. And clean the head tips the same way. Now we'll clean the entrance and exit guides. Make sure that all traces of oxide are removed. And now the components on the way to the capstan. Audio erase, audio and control track heads, stationary guide poles, and the capstan and pinch roller. It's cleaning the pinch roller at this time. And finally the capstan itself. Below the chassis, remove all of the belts and clean them individually while they're off the machine. Here again, the idea is to free the belts from any accumulation of oil or grease. You can inspect the belts at the same time to see if there's excessive wear or scoring that might require them to be replaced. And when the belts are off, clean the drive surfaces for each of the pulleys. There are only 3 points that require lubrication, and at 2,000-hour intervals. These are the supply and take-up reel disc shafts and the counter pulley shaft. Here's the JVC oil container, and you can get a very narrow nozzle by heating the neck of the container with a match or cigarette lighter and stretching it out. Get it as thin as you want, then cut it off. Now we're going to lubricate the take-up reel table. We've taken off the E-ring at the top, and we'll put 1 drop of oil on the shaft, just 1, and replace the take-up reel table. The procedure is the same for the supply reel table. Now the tape counter, the relay pulley, can be lubricated just on the top, just on the shaft, 1 drop. And that's the only points that require lubrication. This chart gives the recommended rate for replacement of major mechanical components, and it's not absolutely necessary that these parts might be replaced, but it's a recommendation to keep the machine in top working order. The up drum assembly, which contains the video head, should be replaced about every 1,000 hours. And at 2,000-hour intervals, all of the rubber tires that have drive surfaces, all the rubber belts, the take-up idler assembly, the rewind idler assembly, and the unload idler assembly, and the pinch roller assembly should be replaced at about 2,000-hour intervals. At 3,000-hour intervals, the audio control track head, both of the motors, and the drum brush assembly at the bottom of the rotary head drum assembly. And at 5,000-hour intervals, the tension band on the supply brake, and the full track erase head. In this section, we'll demonstrate the major electrical adjustments in the servo system and luminance and color processing. The equipment we'll need will include an oscilloscope, a frequency counter, an accurate analog or digital multimeter with as high a current sensitivity as possible. In addition, we need a source of 1.5 volts DC, a battery with a set of clip leads. And we need 2 clip leads, one with a 33 ohm resistor in series with it, and the other with 105.6 ohms. That's a 100 ohm resistor and a 5.6 ohm resistor in series. We'll need several clip leads, and an adapter to go from UHF to Motorola type phono. This adapter is available at Radio Shack, incidentally. And an insulated or small screwdriver for adjustment purposes. The first servo adjustment is capstan discriminator gain. We're using the 3300 for this demonstration. The 3600 is the same, except the test points vary, but you can consult the service manual for them. Now we're going to turn off power and make the following connections. First, a clip lead between test point 12 and chassis ground. Now another clip lead containing a series 33 ohm resistor between test point 14 and chassis ground. Next, a DC power supply, a source of voltage, a battery in this case, 1.5 volts, between test point 21 and chassis ground, positive to test point 21. Now we'll connect our DC microammeter between test point 14 and test point 20. Polarity is not important because we'll be looking for a 0 reading. With this hookup, the capstan motor will be turning slowly, and we must stall it by hand by pressing on the motor pulley during the adjustment. Now with the motor stalled, we'll adjust R76 for a minimum reading in the current meters. We've hooked the 2 meters in series here just for demonstration purposes, and you can see the advantage of having the higher sensitivity of the digital voltmeter. The manual says something about vibration of the meter needle, which is meaningless, really. You're looking for a minimum reading, a null. Next, we'll adjust capstan sampling position. In the 3300, to do this, we'll connect an oscilloscope to test point 12, between test point 12 and ground, and adjust R74 to get a 7.5 volt DC reading. You can use a voltmeter for this purpose as well. Scope here is set up to 1 volt per centimeter. The procedure is different for the 3600. In this case, we'll monitor a waveform at test point 14 on the servo board. We'll put the machine in playback with a normal tape, and we look at this waveform and put the machine in the speed play mode. Now we have to synchronize the scope at a very low sweep speed, 20 milliseconds per centimeter. And we'll adjust R84 so that the top part of that waveform, the top positive going part, the plateau at the top, is 40 milliseconds in duration, 2 divisions in this case. Kind of hard to see because the sweep speed is so low. Then we switch to normal speed and adjust R81 for a duration of 65 milliseconds at the top part of that waveform, the positive going part. Drum discriminator gain is adjusted as follows. We're using the 3300 in this example. First, we turn off the power switch and connect a 105.6 ohm resistor between test point 9 and ground. Those are two resistors in series. Next, we connect our 1.5 volt power supply between test point 19 and ground, positive side to test point 19. Now we'll connect the DC microammeter between test point 9 and test point 18. Under these conditions, the drum might be turning, so stall it by hand. And now adjust R111 for a minimum reading on the microammeter. Now, to check the drum free-running speed and adjust free-running speed, we need to compare two signals. We're going to use a dual trace scope. We'll connect one probe to the video output of a signal generator. We'll connect another probe to test point 5 on the servo board. That's the head switching signal. Now we'll put the machine in the record mode with no input video applied to the machine itself, and we'll adjust R58 until the top waveform stands still. We're synchronizing the scope from the signal from test point 5. And we're adjusting R58 until the top waveform just stands still. That means now that the drum is turning at the right frame rate. Now we're going to adjust the playback head switching point. And for this reference, we'll use the standard alignment tape, and we'll play back the stair-step section of that tape. Now we're going to show you the most difficult way to do it, perhaps, but the method that gives the most accurate results. We're using a dual trace scope with delayed sweep. And we've connected one probe of the scope to test point 5, which is the head switching signal, and that's what you see at the lower waveform. The other probe of the scope is connected to test point 2, and we're looking at video output, playback video output. And now we'll adjust the sweep delay and go to delayed sweep. And now we can see video at the top and the head switching point at the bottom. Now if we trigger from the positive going interval on the head switching signal, we'll adjust R29 so that the switching point, that transition, comes just 3.5 lines before vertical blanking. Okay? Then if we switch the trigger to the negative going slope, we can adjust R33 to put the switching interval the same distance, 3.5 lines before vertical blanking. Record mode switching point is set after the playback mode switching point, and in this case we're going to make the machine imitate the alignment tape, and that is put vertical sync in the same place on the video track. So we'll put the machine in the record mode with a blank tape in place, and we'll compare the same two signals, test point 5 and test point 2, which will be video in this case. And now we'll adjust R9 to put the switching point in the same place, 3.5 lines before blanking. Now the machine will do in the record mode what it had been doing in the playback mode. Now we're going to adjust tracking preset. To do that, we'll record and then play back a video signal. And we'll monitor the RF output at test point 6 on the preamp record board. Now we'll set the tracking control to the preset position, auto position, and adjust R22 for maximum RF output. To confirm that preset tracking is correct, we should remove that cassette and insert the JVC alignment cassette and play it back and confirm that at the auto position, playback output is at a maximum. If it is not, then the control head would have to be moved, and we demonstrated this earlier in the tape in connection with replacement of the audio control track head stack. We'll start the signal processing adjustments now, and the first is cue and resonance in playback of the head inductance. Now, to make this adjustment, we're going to monitor the output of channel 1 FM, and that's at test point 4 on the preamp record amplifier board. We're triggering the scope from test point 5 on the servo board, and we're going to play back the sweep section of the alignment tape. And the first thing we'll do is adjust the damping resistors R34 and R37 so that there is minimum damping, maximum output at resonance. We'll turn R34 fully counterclockwise and R37 fully clockwise. That'll maximize the peak. Now there is a marker, as you can see, a dropout marker at 4.5 megahertz, and we're going to adjust channel 1 resonance, C16, for maximum output at 4.5 megahertz. That's just like a tuning adjustment, and we're tuning the inductance of the head for maximum output at 4.5 megahertz. That's it. Now we've switched the probe to test point 5 on the preamp record board, and we're looking at the output of channel 2. And we'll adjust the damping resistor for minimum damping, and then we'll adjust C18 for maximum resonance at 4.5 megahertz. That's it. After head resonance has been set up on both channels, you can take the alignment tape off, make a recording of a stair-step signal, and play it back and look at the stair-step signal in the bright parts of the picture, the top step for evidence of 30 hertz flicker. If you see such a thing, then it's possible that the two channels are not close enough alike in this area. That is, the output amplitude is not enough alike. So look at both channel 1 and channel 2 and see which one is the smaller, and adjust the other channel so that they both have about the same output in this area. Now that the preamps are set, we'll adjust FM balance between channel 1 and channel 2 to get the same output. Transfer the scope probe to test point 6, and we'll adjust tracking for maximum output first, and then we'll set R45 for the same amplitude from channel 1 to channel 2. Now we'll progress along the signal path to the YC board and adjust the limiters and carrier balance. We'll play back the color bar section of the alignment tape and connect the scope to test point 3, video output in the luminance circuit. And we'll adjust R100, limiter balance, for minimum hash. Now you can see that on the white part of the chip in the color bar signal, and just adjust that part for the cleanest possible line there. You can also look at the monitor screen at this point and adjust for the cleanest looking picture. It's a broad adjustment, not too critical. Now we'll balance the demodulator by moving the test probe to test point 6, the modulator output, and we'll adjust R106, balance 2, to get a clean single line. Notice when it's misadjusted that the top line here spreads, becomes 2. Same thing happens at the tip of sync. But when it's adjusted correctly, we get one clear line at the top. We'll look for the same effect by adjusting R113. Now we're going to adjust for a standard output level and we'll set the scope to test point 3, video out, and play back the color bar section of the alignment tape. And now we'll adjust R120 for 2 volts peak to peak. We have a half a volt per division set up on the scope, so that's 4 divisions. Now, if you're measuring output at the output jack and it's terminated, we will produce 1 volt peak to peak at that point. So if you're adjusting output at the output terminal, you adjust R120 for 1 volt peak to peak. While we're on test point 3, we can adjust the aperture. We can do this by triggering the scope to look at one horizontal line. We're looking at the bottom of the color bar pattern here, and we look at the overshoot on the bottom and adjust R50 so that the overshoot doesn't come down quite as far as sync, just below sync tip level or just above sync tip level, like that. Now we can progress to the modulator adjustments, the record adjustments, and we'll set carrier frequency and deviation. Now we're going to show you a new method that's applicable to both the 3300 and the 3600, and all it requires is a variable source of DC voltage and a frequency counter. The source of DC voltage that we're using at the moment is a 9-volt battery with a 2K pot across it. And we're going to connect the positive output of that simple supply to test point 1, the pre-emphasis out on the YC board. That's the input to the FM modulator. And we're going to connect an oscilloscope to the same test point and set the scope for direct coupling. Now we're going to connect the frequency counter to test point 2, FM modulator output. Now we'll be all ready when we disable the white clip and dark clip. That is, we reduce their effectiveness, take them out of the circuit by turning both R10 and R27 fully counterclockwise. Now we're all set, and we put the machine in the E to E mode and adjust the DC level from our 9-volt battery to get a counter reading of 3.4 megahertz. 3.397 is close enough, certainly. And we're going to look at the scope now, and we'll change the centering on the scope to put whatever level that is at the second graticule line up from the bottom. Now that means that we have a DC level adjusted that will make the modulator work at 3.4 megahertz. That turns out to be pretty close to 4 volts DC, as a matter of fact, but that differs between decks. I'm going to mark the graticule at that point. Now that point on the scope represents 3.4 megahertz. Now I'll raise the DC level, and I'll look at the counter, and I'll look for a reading of 4.4. 4.3, too fast. There's 4.4, and I'll mark the graticule here. Now I have 2 marks on the scope representing the DC level between the deviation limits. 3.4 at the bottom, 4.4 at the top. Now we can disconnect the frequency counter and the variable voltage source, but we'll leave the scope connected to test point 1. That's the input to the modulator. And we'll drive the deck now with a color bar signal. We've synced the scope to look at the lower part of the color bar signal because it shows sync tip and 100% peak white. Now we'll adjust R19, the carrier set control, to put sync tip at the lower graticule mark, representing 3.4 megahertz. Then we'll adjust R30, deviation, to put peak white at the upper graticule mark, which represents 4.4 megahertz. And now the modulator is swinging between 3.4 and 4.4 megahertz. Now we have to reset the white and dark clip. And to do that, we'll look at test point 1 again, and we've set the scope controls so that we have 4 divisions between sync tip and peak white, not looking at the overshoots, just the flat part of sink tip, flat part of peak white. Then we adjust R10, the white clip, for 2.5 divisions for the overshoot, for that white overshoot. There we go. Now we'll change centering so that we can look at the other end of the waveform. And now we're going to adjust R27, the dark clip, for 1.6 divisions for the overshoot, that overshoot hanging down from tip of sink. Now we're ready to set FM record level. And to do this, we'll connect the oscilloscope to test point 1, record out on the preamp record board. Now we'll put the machine in record, that is with tape actually in and moving. We have a color bar signal applied at the input. And we'll adjust R1 for 3.5 volts peak to peak if it's a 3300, 4 volts peak to peak if it's a 3600. Now you can trim the machine for better performance as follows. Consider the 3300. We'll be monitoring this signal, and the nominal value is 3.5 volts peak to peak, but we'll try values of 3, 3.5, and 4. Keep track of where those levels were set by making notes on the tape counter. Then play back that recording and look at the monitor and see which one of the 3 values gave you the best signal-to-noise ratio, and go back and set the record level for the level that gave the best signal-to-noise ratio. Same is true for the 3600, except the nominal or center value is 4 volts peak to peak. Now we can set the E-to-E video output level so that it's the same as the playback level. We'll connect the scope to test point 3 on the YC board, and we'll adjust R62 for 2 volts peak to peak. Scope controls are set here for 0.5 volt per centimeter. The final luminance adjustment is the dropout compensator level. And to do this, we'll make a trial recording and play it back. And then with the oscilloscope connected to test point 4, that's the dropout compensator out, we'll adjust R76 FM level for 0.4 volt peak to peak. Sort of average the noise that we see here to get 0.4 volt peak to peak. And that's test point 4 on the YC board. Now we'll start the chrominance adjustments. And there are 2 subcarrier oscillators in the deck. One is a reference oscillator and the other is a voltage controlled oscillator. And the reference oscillator is done first. Connect the frequency counter to test point 13 on the YC board and play back the alignment tape on the color bar section. And then you adjust C145 to get a reading of 3.79545 plus or minus 10 hertz. It's a kind of a tricky adjustment, but that's why we're not doing it. This is the final reading that we got, and that's certainly within spec. That's only off by 1 digit. The voltage-controlled crystal oscillator is set next, but the unit must be put in the record mode. The frequency counter connected to test point 15, and R185 is set for the same subcarrier frequency. Now there are 2 inputs to the AFC detector, and we have to set the duty cycle of both inputs. We'll put the unit in the record mode. We'll connect our oscilloscope to test point 17, and then we'll just adjust R225 for a duty cycle of 1 to 3. We've set the scope up so that we can get 1 division on the negative going part of the waveform and then 3 divisions on the top of the waveform. And that sets the correct duty cycle. Now to the second stage of the AFC detector adjustment. We're going to use a dual trace scope, and we're looking at test point 17 now, and we're using channel 2 of the scope. On channel 1, we'll look at test point 18. Now we'll go to alternate and we'll see the both of them together. What we're interested in is the trigger point here, and we'll go into the add mode. And this is the area of interest, so we'll use delayed sweep. And now the delayed sweep is 1 microsecond per division. And this part, following that negative transient, should be 2 microseconds wide. And we'll adjust R222 for that 2 microseconds. Okay, now we're ready to set playback color balance. And we'll connect the scope to test point 7, playback color out, on the preamplifier record board. And we'll trigger the scope from test point 5 on the servo board and adjust R44 to equalize the output from both heads, like that. Keeping the scope at the same test point 7, we can now set playback color level. And we'll adjust R58 for 0.4 of a volt peak to peak at test point 7. This is 0.5 volt per centimeter. Now we'll set the main converter balance. These are balance converters, and we'll connect the oscilloscope to test point 8 and play back the color bar section of the alignment tape and adjust R137 for balance. And you'll see balance by looking at the areas where there's no chroma, in sync just before burst, and adjust the balance part to get as thin a line as possible there. We're now ready to adjust color output level, and we'll monitor the video output of the machine at test point 3. And we'll play back the color bar section of the alignment tape and adjust R136 for a burst amplitude of about 0.5 volt. Or as an alternative, the cyan bar, top of the cyan bar should be just below the 100% white bar in the lower part of the picture. Now the final steps are to adjust color record balance and color record level. Now we've already adjusted color playback balance and color playback level, and now we're going to make the record circuits come out with the same numbers. So we'll monitor the output, color output on the preamp record amplifier board at test point 7. This is where we're looking now. And we'll have to make a number of trial recordings with various settings of R27, that's the color record balance. Then we'll play back those recordings, and what we'll be looking for is the same output level between A and B heads. And we know that the machine is right in playback. Now we have to make it the same way in record. Similarly, if the color level is too low in playback, then we'll advance the color record level, R2, play the recording back until we get the same level in playback from our own recordings. That is 0.4 of a volt peak to peak at test point 7. Some words are in order now about reassembly. Most of it is just a reversal of what you did when you took the machine apart. And we've put back all of the covers except the top. And the only thing that's somewhat critical is the reinstallation of the cassette holder. That's a little bit tricky, so we're going to show you how to do that. Now, first of all, before you put it into place, the cassette holder should be up and it is fully extended. Don't collapse it and try to put it in the machine. The next thing you have to look at is that tab. Now, that tab must fit between this lever, which is linked to the eject button. Now, normally when the machine is flat, that lever liable to fall forward towards that bulkhead you see at the bottom of the picture. So push it back by hand or with a screwdriver, just so that there's a space between the vertical part of that lever and the bulkhead. And that tab on the cassette holder has to go between those two spaces. Otherwise, the cassette holder will not eject. There's that tab on the cassette holder that has to go between the lever and the function block wall. And just to the left of the tab, there's a phosphor bronze spring, and that spring has to bear against the rear wall of the function block as you put the holder in place. Now make sure the holder is up, and as you install it, be careful of the foot. It goes between the two parts of the counter belt, and make sure it doesn't catch on the belt. Make sure the cassette holder is up, and it'll go in easily without catching. Okay, we put the cassette holder in place, and we've installed the 4 mounting screws in the feet, but we haven't tightened them. And now we're going to use the jig, the part number for the jig. This is a new jig used to position the cassette housing before the screws are tightened. And it's held in this fashion and inserted in place of the cassette and pushed all the way back. And then the cassette is lowered, pushed down, and push that jig down so that it seats over the reel tables firmly. And that'll keep the cassette from moving around, and it's in precisely the right spot. Then the screws can be tightened and the job is finished. In the remainder of this tape, we're going to look at some basic troubleshooting information, and we'll try to cover the mechanical system control, both capstan and drum servo systems, and the color processing. The Metricon system control board is located in the front of the deck, just to the left of the channel selector switches, and it's located on the schematic on page 1018 in the 3300 manual in this area. Now, the system control coordinates inputs from various places. The function selector buttons on the front panel and automatic stop functions. Now, this is the function selectors on the front panel. There's a 12-volt in, and these micro switches S2, 3, 4, and 5 deliver 12 volts out to the system control board when those functions are selected. The operate switch is closed if any function is selected. So fast forward, play, rewind puts 12 volts out on the operate line. And the last switch over here, S1, is also operated by all function. That's a relay control for a relay in the power supply board. Now that's one of the sets of inputs to system control. Now let's take a look up here at the top. System control also coordinates various functions which tell us the status of loading. For example, S7 closes the moment that the loading arms are away from the home position. So at the instant loading starts, this switch closes and we get 12 volts on this brown line that will be there until unloading is finished. And this switch closes for after loading stop, the end of the loading function. Now, just to the right of that, there are some sensors. These are the photo transistor sensors for the start of tape and end of tape. And these have high outputs, 12-volt outputs that go out on these green and blue lines to indicate that the start of tape has been reached or the end of tape has been reached when we get a plus 11 volts on either of these two lines. And that is when these photo transistors are illuminated. In addition, through this diode gate, there's this transistor X1, which is held on by a return from the cassette illuminating lamp. That is the lamp that illuminates the photo transistors. If the lamp should burn out, then this transistor would turn off and we'd get a positive volts output on both of the sensing lines to shut down the machine. And in addition, X1 is held cut off by the cassette in switch, S12. As soon as the cassette is dropped in place, then that switch opens and this transistor can come into conduction. Now, just to the right of these sensors, there is one more sensor, and that is the take-up sensor. Now, that's magnets embedded in the relay pulley from the take-up reel table to the tape counter. And when that magnet is turning, we get an AC signal on the take-up sensor out line that goes to the mechanism system control. Now we'll take a close-up look at the system control board itself. Now the system control board has two outputs. One is the motor control voltage that's fed to the servo board that allows both capstan and drum servo motors to operate. And the other output is off here to the right. It's the stop solenoid, which disengages any function button that might have been selected if an automatic or stop is indicated. Now, the system control board is also broken up into two major areas, above and below this operate line. This area at the top monitors what's going on at the take-up reel sensor and the drum to see whether or not it's possible to keep the motors operating. The lower section down here in this area monitors the auto stop functions to trigger auto stop. And the heart of the system is right here for troubleshooting purposes. This is IC4, and this is really where everything is brought together for troubleshooting purposes. This is a NAND gate, and the only thing that you need to know about NAND gates is that the output is high unless all of the inputs are high. If all of the inputs are high, then the output drops to 0. And that's the only thing that you really need to know for troubleshooting purposes. Now, this output has to be at 0 in order for the motors to operate, and at 0 to keep the automatic stop solenoid from functioning. So under normal conditions, when the machine is running normally, we'd have a 0 at pin 10. And if we look down here just below, we'll see that that goes to this transistor. It cuts this transistor off, and if this transistor is cut off, its collector voltage rises to the supply voltage, and that output goes to the servo system. That output is the motor control that goes to the servo system. Okay, let's get back now to IC4, and this is where we're going to look. If we don't have a 0 at this point, the motors are not running, and the stop solenoid would have been energized. In order to get a 0 here, we have to have highs at all three inputs. Now, there's normally a high from IC2. Now, this is the auto stop section, and if something has not indicated that stop should be initiated, this output is normally high. The center simply goes to 12 volts, so this is also normally high. And we're going to get a high at the top, pin 12, and we'll examine that in detail just now. One comment I should make is that in order to measure these voltages, you need a high impedance voltmeter, FET, VOM, or a digital voltmeter. If you measure this voltage, for example, at pin 13 with a 20,000 ohm per volt voltmeter, you'll load the voltage down and you might even trigger auto stop. Okay, in order to get the motors to operate now, we want to look for a high at pin 12 of IC4. The other two we'll consider high for the moment. Now, before any of the functions are selected, we'll be taking a high from this capacitor, because while the machine is in idling waiting for a command, this transistor is cut off, and the capacitor C1 charges through D2, so it charges up to B plus and stays there. Now, when we press any of the function buttons, we get a high on the operate line, and that saturates this transistor. It goes to, the collector voltage goes to 0, disconnects the diode from the system, and now this capacitor holds that charge for a wee dab, but it begins to discharge, and that voltage runs down like a clock. But that initial DC voltage gives us a start. It gives us the high we're looking for at IC4 to get things going. Now, to sustain that high, to keep it going, we need a high from IC2 pin 6. And that's what we're going to look at next. We're going to have to get a high at IC2 pin 6, or in a few seconds, C1 will lose its charge, we'll get a low here, a high at the output, and that will kill motor control voltage. It'll also initiate auto stop. You'd hear the auto stop solenoid pull. So we're going to see how we go about getting a high at the output of IC2 pin 6 in order to keep things going. Okay, now we'll progress backwards from IC2, and we're looking for an output from IC6. Now, running back, we see at the top there are two AND gates, and let's skip them for a moment because they both will have high outputs. Let's suppose we've selected fast forward. That means there's no high at the play. So we'd have a low input to both of these gates. Both of these would be high. So the top inputs to IC2, pins 5 and 4 are high. Now we have to concentrate on what we're getting at pin 3. And that is a coordinated input of two sources. The input to this NAND gate at pin 8 is the head switching pulse that comes from the servo system, and that's fed into pin 8. If the head drum is turning and we are generating the head switching signal, we will have a flip-flop signal into pin 8. In addition, at pin 13 of the next NAND gate, we have a 1 hertz pulse in from the take-up sensor, that AC signal that comes through X3. So if the take-up reel is turning and tape has not broken and there's nothing jamming the drive to the take-up reel table, we'll have a 1 hertz pulse into pin 13. Let's consider the take-up sensor first. If tape broke or the take-up sensor or take-up reel table were not turning for some reason, then this transistor would be on. We'd have a 0 here but no signal, and that would be an off or a low into pin 13. We'd get a high from 11, and as soon as we get all three inputs to IC2 high, we get a low in this point. Now that low is transmitted down to X4. We'll get a high here. That's going to stop the motors and, as we'll see, initiate auto stop in this part of the circuit. Now let's go back one step to IC1 and monitor the head switching signal that comes from the head drum assembly. And that's monitored in the play mode because we'd have 12 volts on pin 9 if the play function is selected. And we'd be getting the 30 hertz flip-flop signal into pin 8, and pin 10 would also be changing at a 30 hertz rate. But if we lose the drum pulse signal, if the rotary head drum assembly were jammed by tape or something like that, then this signal would go high at pin 8. We'd have two highs. Pin 10 would go low. That would really disable IC1, and pin 11 would go high. Now we have three highs at IC2. Pin 6 would drop to 0. That would cut off the drive that will eventually give us motor drive control and would also initiate auto stop. Here's what the signal at pin 6 of IC2 looks like. Now you should have the combination of the take-up sensor, which is a 1 hertz signal, and the 30 hertz square wave from the head switching signal. And the scope is slowed down now to about 10 milliseconds per centimeter or even slower, and you can see those 30 hertz square waves coming and disappearing at about a 1 hertz rate. And unless both of those signals are there, auto stop will be triggered. We'll just stall the take-up sensor by hand, and you'll see one disappear. Now we have nothing, and stop would be triggered. Now we'll take a look at the end of tape sensors and the search sensor in rewind. And to do that, we'll go back once again to IC4, the heart of the system. And remember that all three inputs must be high in order to get a low here, so that the motors will operate and the stop solenoid will not function. Now we're going to trace the bottom line back from pin 11, and this is the auto stop area. So we need a high here normally. IC2, this section is hipped as an inverter. All inputs are connected together. So to get a high here, we need a low here. And in order to get a low at pin 10, all three inputs 11, 12, and 13 must be high. So normally, unless we've run into an automatic stop function, you can check all three inputs here and they should be high, at around 11 or 12 volts. Now let's consider one of the automatic stops, either in fast forward or in play, and that's IC3 here. Now, pin 12 of IC3 is marked rewind with a line over the top. That means not rewind. So if rewind has not been selected, we got a low here and we have a high. So we have a high normally at pin 12 unless rewind has been selected. Now if we run into the end of tape sensor, if the clear leader at the end of the tape uncovers the end of tape sensor so that it's illuminated, we get a high on pin 13 and we get a low here then. Now a low here will give us a high at the output, a low at pin 9, and a low to one of the inputs to IC4. That'll give us a high at pin 10. That'll trigger auto stop and also turn off the power to the motors. In the rewind mode, the lower input, pin 11 to IC2, is what we'll be concerned with. And if we trace that back, we get to this gate, or actually the two lower lines go to these two gates. Both of these gates function in the rewind mode. If the rewind button is depressed, we have a high here, and it's on pin 5 and pin 2. Now, if we should reach the start of tape in the rewind mode, if the clear leader at the beginning of tape should be uncovered, then we'd have a high at this point and a low that would trigger auto stop. And then back here, if we have the search switch on, and if we're in the rewind mode and we get to a counter reading of 000, we'll have a high here at that reading. Two highs would make a low at pin 4. We'd have a low at the center input to IC2, and we'd trigger auto stop in the same way.